So you've now seen how streetlights and the lights on the main walkway behind me work. You've seen that there's two types of charges. We've got positive charges and negative charges. An electron is an elementary charged particle with a negative charge of 1.602 times 10 to the minus 19 coulombs. Objects become charged by gaining electrons and becoming negative, or losing electrons and becoming positive. We've seen that opposite charges attract while light charges repel. The size of this attractive or repulsive force is described by Coulomb's law, which can be written mathematically as K Q1 Q2 over R squared. K there is Coulomb's constant. After looking at static charges, we started to look at what happens when charges move. We saw that when we have moving charges, we have an electric current. We had a little bit of a discussion about how electric currents really are made up of electrons moving, but the electric current is conventionally taken as moving in the opposite direction to which the electrons move, and this is just because of history. When current was first discovered, it wasn't realized that it was actually the negative particles that were moving. So we saw how the size of the current is related to the number of charges which is passing a point. So we can write the equation that I, the current, is equal to Q, the charge, divided by T, the time. We saw that the voltage and current are both proportional to the resistance in a circuit. So this relationship can be shown through Ohm's law, which can be written as V is equal to IR. That is, the voltage is equal to the current times the resistance. We saw that there was different ways that we could wire up circuits. So in a series circuit, the current passes sequentially through each of the components. In a parallel circuit, we have branches, with some of the current going through one branch and the rest of the current going through another branch. Electric circuits also require power. So power relates the amount of energy which it uses to time. So power is given as energy divided by time. If we want to calculate the power dissipated by an individual circuit element, we can calculate it using the formula P is equal to VI. That is the amount of power that a circuit component uses is equal to the voltage drop across it times the current flowing through it. Lights convert electrical energy into light and heat energy. Very efficient lights will convert most of the electrical energy they receive into light energy with very little heat energy produced. Incandescent lights used to be very common but are now being phased out because they're very inefficient. So incandescent lights produce a lot of heat energy and not too much light energy. LEDs, on the other hand, are very efficient. So LEDs are now commonly used in traffic lights. They're not quite intense enough to use for street lights. So street lights tend to be sodium vapor lights, like the lights behind me, or metal halides. So sodium vapor lights and metal halides are very efficient, and they can also be very intense. Finally, we had to look at how streetlights know how to turn on. So the streetlights have a photodetector in their top, which makes use of the photoelectric effect. When photons of light fall on a piece of metal, if they have enough energy, they can cause an electron to be released. Within the photodetector, these released electrons are detected. Once the sun goes down, light is no longer falling on the photodetector and the electrons stop being ejected, and so the photodetector detects this and the street light knows that it is now time to turn on. So now that you've finished working through the interactive lecture, it's time to have a go at the tutorial problems. Have a go at them yourself, but then if you do get stuck, there are solution videos which you can use to review the answers.